Welcome back, Virtual Physical Science. So we learned the basics of electricity last week, and now we're going to use it to talk about circuits, because electric circuits are the way that we apply the knowledge that you learned about last week most often around the house and the classroom. An electric circuit is just a closed loop of some kind of conducting material that carries a current. Most electric circuits are going to contain three types of things. First, a source of some kind of electrical energy, usually a battery or the outlet of a wall or a generator, something like that provides the energy. And then wires, something conducting, copper, aluminum, something like that carries the current from one place to another, carries the current from the source to the load. And the load is the device powered by the electricity. It's the whole point of having the circuit in the first place, like a light bulb, an iPod, computer, or something like that. Here's a simple example. You can see the source of electricity, my battery here, and you can see the load, the light bulb here. And in between I've just drawn a wire, and that's the conducting material that's carrying the electrical current from the battery to the load, to the light bulb. The current flows from positive to negative. So in this diagram it flows as indicated by this arrow here. But because electrons are negatively charged, they actually flow the opposite direction. This unfortunate situation is the result of the fact that when Benjamin Franklin first discovered that there were two kinds of charge, positive and negative, he decided to call the wrong one positive. If he had called them the other way around, then we would have said all along that electrons have positive charge and current and electrons would move the same way. Unfortunately, he chose the other way, and we're stuck with that historical accident. What happens if we add two more light bulbs, here and here? Now we have the same amount of current powering three light bulbs, so they're not going to be as bright, first of all. Second of all, this is what's called a series circuit. A series circuit only has one path for the current to follow. So the current has to go from the battery to the first light bulb, then to the second light bulb, and then to the third light bulb. The word series means in a row, things arranged one after the other, and that's the idea in a series circuit. The current has to flow through each load to get to the next one. It doesn't have any option. There's no other way for it to go. So what happens if something goes wrong and one of these light bulbs burns out? Well, as indicated by this red here, this light bulb has burned out, and now all three light bulbs are going to turn off. The current stops, the electrons stop. Because it's a series circuit and the path has been broken, because this light bulb burnt out, then the only path that the current can take has been cut. There's what's called an open circuit, meaning the loop of current that was flowing from the positive terminal of the battery to the negative terminal of the battery is now cut. There's a hole in it, and the current can't flow if there's a hole in the loop. So because of that open circuit there, where that light bulb burned out, all three bulbs are going to go out. They're not going to be lit anymore. The other two aren't broken, like the one that's red there, but they won't light up because there's no current flowing. So that's a disadvantage for a series circuit. A series circuit is simple and easy to make, but it has this disadvantage. One bulb goes out and they all go out. Well, here's the alternative. This is what's called a parallel circuit. In a parallel circuit, there's more than one pathway for the current to follow. I've tried to show in green how the current coming out of the positive terminal of the battery splits and goes in multiple directions. At this first junction of wires here, the current goes to the left and down, and the same thing happens at this second junction here. And then the current rejoins at these junctions here and here. Okay, a parallel circuit is more difficult to build, it's more complicated, but it has advantages. The first advantage is that if we happen to have the same situation we had in the last circuit, if one of the bulbs burns out, the other two won't go out. I've tried to represent a burnt out bulb by the red again in the middle. No current is flowing there because that part of the circuit is now broken, but because there are other pathways for the current to follow, the other bulbs don't need to go out. The current can still flow down the other two branches of the circuit, and so those two bulbs will stay lit. So this is an advantage for a parallel circuit. Here's a very similar circuit. I've replaced the light bulbs with these blue squiggly lines. In circuit diagrams, those squiggly lines are known as resistors. They could be light bulbs or toasters or iPods or anything that requires power, anything that resists the flow of electricity. And I wanted to show you something interesting about a parallel circuit. If we have a 3-volt battery here, then what that does is it makes sure that this part of the circuit is 3 volts higher than this part of the circuit. And in fact, since the whole top part of the diagram is connected by wires, this entire red part here has the same voltage, and this entire green part here has the same voltage. Now these 3 resistors are not the same. The one on the left is a 10 ohm resistor, in the middle we have a 20 ohm resistor, and on the right a 30 ohm resistor. Because the one on the left has the lowest resistance, more current is going to flow through there. The one in the middle is going to get a middle amount of current, and the one on the right with the highest resistance is going to get the least amount of current. It's kind of like if you imagine a pump pushing water, which I've tried to represent in this bottom diagram here. Imagine that these tubes are filled with water and that the pump on the right is pushing the water around. Well, most of the flow in this set of pipes is going to go through the fat pipe on the left because it offers the least resistance to the flow. The skinny pipe on the right is going to be very hard to push water through, and so very little water is going to flow through there. While a big resistor is kind of like a skinny pipe like that. It's hard to push electricity through it, and so not much current will flow. So resistors and light bulbs and all kinds of devices, they use up electrical power. And there's a simple formula that relates the power used by an electrical device to the current flowing through it and the voltage across it. The power is just the current times the voltage. P equals IV. Remember, I is the symbol for current. Power measured in watts, current measured in amperes, and V measured in volts. 1,000 watts is known as a kilowatt. Let's say we have a TV that runs on a 220 volt plug from the wall that draws 0.2 amps. How much power does it use? Well, that's easy. The power is just the current 0.2 times the voltage 220. That turns out to be 44 watts. So this TV uses 44 watts of power. Sometimes too much current or too much power flows through a circuit, and we want to protect sensitive devices from all that extra power. That's what fuses and circuit breakers are for. A fuse is essentially a very small piece of metal that when the current flows through it, if the current is too high, it will heat up and melt. And if it melts, then it won't be there anymore, and the hole in the circuit that it leaves behind will stop current from flowing. So it's a safety measure. A circuit breaker works in a similar way, but instead of melting, the heat, if the thing gets too much current through it, it heats up and bends, and that bending causes it to move out of the way, and the circuit is broken in that way. So these are both safety measures that are used to protect from power surges. They become very useful in a place like Tana where the power flow is very uneven. So we talked about electrical power, and power is basically the rate at which energy is used. How fast do you use energy? So you can use that to figure out the energy if you know the power. Power is energy over time, the rate of energy use. So energy is power times time. Typically in household applications, electrical energy is specified in units called kilowatt hours, which is a kilowatt or 1,000 watts times an hour. If you use an appliance that takes 1,000 watts of power for 1 hour, that'll be 1 kilowatt hour of energy. There's a nice example on page 214 and 215, I think, that helps you to work out using these equations. But they're both pretty simple equations, the one for power and the one for energy. Alright, for homework in this section, I'd like you to read 7.3 and on page 215 answer questions 1 through 5. Good luck, guys.